All right, so welcome back, folks. I apologize. I don't quite know what happened with the video yesterday. The computer just kind of shut down on me. I would like to go ahead and continue with that discussion of the structure for the hydrogen cyanide here, and then being able to identify the types of bonds that hold these three atoms together, and I be able to identify the bonds and the hybrid orbitals, the orbitals that go into making those bonds, and the interactions of those orbitals. Okay, um, so let's go ahead and let's pick up with where we left off yesterday. Okay, so remember, when you are asked to identify the hybridization of these atoms here, what you need to be able to do then is to be able to identify the arrangement of the electrons around each of these atoms when they bond together in a molecule such as this one here. So you have to identify the electron domains first. Make sure you go ahead and do that. From that, then you can determine the geometry of the electron geometry around each one of those atoms. And from that electron geometry, we can describe the hybridization. Once we have the hybridization of the atoms, we can see then how those orbitals will overlap, how the hybrid orbitals will overlap, how these orbitals interact with one another. And based upon that interaction, we can then go ahead and characterize the bonds then as either being a sigma bonding interaction or a pi bonding interaction. Okay. All right, so to start out with, what you need to be able to do is you got to draw the Lewis dot structure for each one of these atoms first. And so the Lewis dot for the molecule first. And so the Lewis dot structure for hydrogen cyanide, then again, if you don't remember this, make sure you go back and you practice this in chapter 8. Okay? Single bond between carbon and hydrogen, which means that for this particular bond here, you have 2 electrons that are being shared between those 2 atoms. You have a triple bond here between carbon and nitrogen, which means that 6 electrons are being shared between carbon and nitrogen. And you have a lone pair out here as well. Okay. All right. So that means then when we go to characterize this single bond and this triple bond here, we have to show then where the electrons are located and what orbitals these electrons are located in, and how then how do those orbitals overlap in order to form these bonds here. And so remember, each one of these lines here represents a pair of electrons that are being shared. So therefore, there's 6 electrons here between carbon and nitrogen, and 2 electrons here between carbon and hydrogen. Okay. All right, so let's go ahead, and where we left off with yesterday is we described the hybridization of each one of these atoms first. We started with the carbon atom here, 2 electron domains. Here we have a pair of electrons here. We have 3 pairs here, but remember the triple bond counts as an electron, 1 electron domain, in the same way that the hydrogen, the single bond here counts as 1 electron domain. So you have 2 electron domains around carbon. Whenever an atom has 2 electron domains, the geometry then is going to be linear. 180 degrees between the electron domains. And when you have a linear arrangement around a particular atom, we know then that it's going to be sp hybridized. So carbon then is an sp hybrid or sp hybridized atom. Okay. We can say the same thing about nitrogen here. And so when we go about characterizing these bonds here, you have to be able to identify the hybridization for all of the atoms involved in the molecule. And so with that said, then around nitrogen, we have 2 electron domains, one that's bonding and one that's non-bonding. The bonding domain comprises 3 electron pairs, but again, this counts as 1 domain. Okay? So you have 2 electron domains around the nitrogen, which means then it's going to be a linear electron geometry around the nitrogen as well. And if it's a linear electron geometry around the nitrogen, nitrogen is also sp hybridized. So you have an sp hybridized nitrogen, and you have an sp hybridized carbon. Okay? And I'm sorry, let me go ahead and clean that up a little bit. Whoops, sorry. Clean that up. Okay, sp hybridized nitrogen as well. So you have an sp hybridized nitrogen, sp hybridized carbon. Both of these here are sp hybridized. Sorry, what's going on here? An sp hybridized nitrogen as well. Hydrogen is in this interaction, hydrogen is not hybridized at all. Hydrogen has an s orbital, and you have that 1 electron in the 1s orbital right there. So hydrogen is not hybridized, and you got to make sure you keep that in mind. Okay, so there is no hybridization on the part of the hydrogen. So now we have characterized the hybridization or the lack thereof for every one of these atoms here. Okay, so let's go ahead then and let's characterize the bond then between each one of these atoms. Okay? Right. So first of all, then, we have. we have then an sp hybrid orbital here. So we're going to take one orbital at a time. Okay, so it's going to be a little bit slower, but I want to take one orbital at a time. So this is one of the sp hybrid orbitals. Remember, an sp hybrid orbital, the atom takes one p orbital, hybridizes with an s orbital of that s orbital. So therefore, you end up with two sp hybrid orbitals. I'm only showing you one right now. We'll deal with the other one in just a moment, okay? But this is the sp hybrid orbital around the carbon. This is one sp hybrid orbital. And so carbon takes this particular sp hybrid orbital, one of them, okay? And it's going to hybridize it with, and it's going to interact with the s orbital from hydrogen. So make sure you remember then that within this sp hybrid orbital, there's going to be one electron. Okay, so in each one of these hybrid orbitals, okay, remember carbon has four valence electrons, and when it hybridizes, it's going to place electrons into that hybrid orbital, as many that forms. So one of the electrons, one of the four valence electrons will fall into the sp hybrid orbital here. Okay. Hydrogen has one valence electron, it only has one electron, and so it's going to be in the 1s orbital. So this is going to be the 1s orbital for hydrogen. The overlap here between the 1s orbital and the sp hybrid orbital from the carbon, this forms the bond. This is the bond that forms, and that's the single bond right there. That's the single bond right there that forms between the carbon and the hydrogen. That interaction there, if you can draw a straight line to the interaction. And if you can draw a straight line through that interaction, then we then have a sigma bonding interaction. So this single bond then is a sigma bonding interaction. That single bond represents a sigma bonding interaction. And so therefore, the single bond here is a sigma bond involving an sp hybrid orbital from the carbon and a 1s orbital from the hydrogen. Okay, and so there it is. We've characterized this single bond right here between hydrogen and carbon. Okay. All right. So let's go ahead and let's tackle this triple bond here between carbon and nitrogen. Okay. All right. So carbon has a second hybrid orbital. Carbon has a second hybrid orbital. It has a second sp hybrid orbital, and there it is. Okay. So let's go ahead and let's deal with this. So this is the second sp hybrid orbital here. This is the sp orbital, the second of two, and it's going to have one electron sitting in there. So it has one electron sitting in that particular orbital as well. Okay? And so remember, this triple bond represents 6 electrons that are being shared. Each line then represents a pair that's being shared. And so it doesn't matter which one we pick, but let's just arbitrarily say that let's form this bond right here. Okay? This bond here forms then between this sp hybrid orbital, okay? And so this electron has to be shared with nitrogen somehow. And so how does nitrogen share? How does nitrogen contribute to this bond here? How does nitrogen contribute to this particular single bond here? Well, remember, we said nitrogen is also sp hybridized, okay? Which means that nitrogen has a sp hybrid orbital. So this hybrid orbital comes from the nitrogen. Okay, this is a nitrogen sp. Okay, so let's go ahead and write that in. Okay. This sp hybrid orbital comes from the nitrogen. Okay. So therefore, this is also sp hybridized. Nitrogen will have its electron in there. Okay, so it's going to put one electron there. And so there we have then an overlap. So if you take a look at this here, the overlap here between those two electrons within this hybridization here forms the bond then, forms one of the bonds of that triple bond. And if you notice here, we can draw, again, a straight line through both of those hybrid orbitals. And so therefore, this particular bond here, okay, this interaction here will be a sigma bonding, sigma bonding interaction. Okay. This also then is a sigma bonding interaction. Okay. Which means then one of the bonds here of the triple bond is a sigma bonding interaction, but that's only one. That's one of the 3. Okay? So what about the other 2? How are the electrons being shared here? Well, make sure you understand then that there are no more hybrid orbitals that form. There are no more hybrid orbitals. So whenever an atom is sp hybridized, you only get 2 hybrid orbitals. So carbon's taken one of its sp orbital and used that to form this sigma bond here, this single sigma bond with hydrogen. Carbon's taken its other sp hybrid orbital to form one of the triple bonds with nitrogen here. Okay? And so where are the other electrons? Okay? Well, remember, with sp hybridization, when we talk about sp hybridization, what happens then is it's going to be one s orbital plus one p orbital from the atom, which leaves then three unhybridized, two unhybridized p orbitals that are still sitting here. So carbon then has two p orbitals that are, I'm sorry, there's the other sp hybrid orbital. Let me go ahead and take care of that one really quickly. There is the other sp hybrid orbital from nitrogen. And then we'll talk about this in just a moment, but just try to answer this in your head real quickly. If one electron, if this sp hybrid orbital from nitrogen has one electron, it uses that one electron to form this bond here, one of the triple bonds here. What's in this second sp hybrid orbital for nitrogen? What's sitting inside this sp orbital, hybrid orbital for nitrogen? So we'll get to that in just a moment. Okay. All right. So let's continue on with this triple bond here. Okay. And so with that triple bond, then we're going to have sorry. Okay. Right, so like I said, carbon then has two p orbitals, and let's go ahead and draw that one in here. Okay, so this is going to be a p orbital. This is an unhybridized p orbital. This is going to be the 2p orbital. Okay, this is, and we'll call this the 2p orbital on the y-axis. Okay, so that's going to be the 1p orbital that's unhybridized. Let's just, for the sake of argument, say that the p orbital here that it used to hybridize is on the x-axis. Okay, so that means then it has a second p orbital. Okay, so carbon then has a second p orbital, and so does nitrogen. So this is going to be the 2p orbital. Okay, so since nitrogen is also sp hybridized, okay, nitrogen also has a p orbital that is unhybridized. Okay, so let's go ahead and draw that in. So this is going to be from the 2p, we'll again call that y. That's an unhybridized 2p orbital from the nitrogen. Okay. Now with that said, then carbon also has a second p orbital. Okay, that second p orbital then, and let's go ahead and take care of this one really quickly. That second p orbital then is the it's going to be then the 2p orbital along the z-axis. Remember, there is a p orbital on each of the axes, one along the x, one along the y, one along the z. So therefore, carbon then has these two p orbitals that are unhybridized. We're going to see then that it's going to be the same thing with nitrogen. Nitrogen also then has a p orbital that is unhybridized. Okay? And so this is going to be the 2p orbital along the z-axis as well. 2p orbital on the z-axis. So this p orbital here and this p orbital here are parallel to one another, as well as this p orbital and this p orbital as well. So those are parallel. And so with that said, then make sure to understand then that the nitrogen here in each of these p orbitals, nitrogen will have also an electron here and an electron here. And that electron can be either found here or here. This electron can be found either here or here. The same thing holds true with the nitrogen. Carbon. Carbon's going to have the third of its 4 valence electrons here, as well as here. And again, there are the electrons for the carbon. So there are the 4 valence electrons. You have 1, 2, 3, and 4. Okay? So how then do these two bonds form for the triple bond? You can imagine this happening here then. The 2 p orbitals here that are parallel to one another, they will share. The electrons will flow across those here. That electron will move from one side to the other, forming then an interaction here. This interaction here is what we refer to as the pi bonding interaction. Why is it pi bonding? Because these two orbitals line up side by side. If this is a linear interaction here, this is a side by side interaction. So this is a pi bonding interaction, okay? Which means then that the two electrons then, the one electron from the 2py, the 2p orbital from nitrogen, and the one from the 2p orbital from the carbon, they are moving across from one side to the other. So this interaction here accounts for this second of the third this second of the third bond in second of the three bonds in this triple bond here. Okay, so one of these bonds will be a sigma bond, the second one will be a pi bond, and if you take a look at the third one here, that will form, if you take a look at that, between the two electrons from the 2pz. Okay, so again, this orbital and this orbital, they're parallel to one another. So these two electrons here, they will move across along this one here. So therefore, this will also be a pi bonding interaction. Okay. So you have then two pi bonding interactions in this triple bond. Okay, so in the triple bond itself then, one of those bonds of the triple bond, one of those pairs will be shared by a sigma bonding interaction. The remaining two pairs will be shared via a pi bonding interaction. So essentially then with the triple bond, you'll have one sigma bond interaction and two pi bonding interactions. And so that's how we can account then for this triple bond here. So we can characterize this triple bond then as this bond then between carbon and nitrogen as a triple bond. And in this triple bond, then one of the three will have a pi bond, a sigma body interaction, and the remaining two will be a pi bonding interaction here. Okay, all right. So that's how we can account for this interaction here. Okay, all right. So with that said, then, how then could my question that I asked you then is, what sits in this particular this sp hybridized orbital here for nitrogen? Okay, well, remember, nitrogen has 5 valence electrons. We've accounted for three of them are involved in bonding. So you have 1, 2, 3. That means then the remaining two valence electrons will fall right here into this hybrid orbital there. Okay, so that's where the remaining two will go. So therefore, these two electrons here, these two lone pairs, sit in an sp hybrid orbital. Okay, and so there we have it. We've accounted then for all of the interactions. We've accounted for where all the atoms will be for each, all the electrons will be for each one of these atoms, what the electrons do for each one of these atoms, and we've also talked about how then the bonds form. Okay. So this is the level of detail that you have to be able to include when you characterize the bonds for the within a molecule. Okay, and so please make sure you write this down, and hopefully if again when you draw this here, I don't expect you to draw these bubbles here. You don't have to draw those bubbles, you don't have to draw those shapes, but you need to be able to do them. And I'll finish up here really quickly, folks. What you need to be able to, with some problems for you to practice with, okay, what you need to be able to do is draw the Lewis dot structure. Okay, you need to be able to identify the hybridizations here for each one of these atoms. From that hybridization, then hopefully you can get to the point where you can see then that this sigma bond then, and again, we'll practice doing this. This sigma bond here is going to be, this single bond here will be a sigma bond, and I will abbreviate that with the Greek letter sigma, lowercase sigma. So this is a sigma bonding interaction, and that's what you have to be able to do. And then with this one here, then you should be able to identify that. It doesn't matter which two here, you have to be able to identify that 2 of these will be pi bonding interactions. You have the pi bonding interactions. I'm sorry. Okay, and then one of these here will be sigma bonding. Okay. Okay. And then make sure you recognize then that this will be a sp-sp overlap. This is going to be p orbital overlap. This will be a p orbital overlap. This is going to be a sp with an s orbital overlap, and the last sp hybrid orbital for nitrogen is going to be occupied by these electrons here. Okay, all right, that's what you have to be able to do for the purposes of the AP exam and for our class as well. So that's the level of detail, folks. That's the level of detail that you have to be you have to feel comfortable doing. So what I'll do is I will post this slide here for you. I'll post this slide for you that you can use to help you study, okay, and make sure you take a look at it. But let's continue on. I want to do a couple more before our time is up. Okay, so let's go on and let's take a look at a couple of problems that I want you to practice. Okay, so I want you to practice doing a few of these problems here. All right, so number 6 here, I give you 5 molecules, and I want to do 4 of these 5 here together, okay? And then I want you to, we'll try to do as many as we can, and I'll leave it up to you to do the remainder, okay? So what I'd like you to do then is I want you to take nitrogen, so, oops, sorry. I want you to go ahead and I want you to do nitrogen first. Okay, I want you to draw the structure for nitrogen, I'm sorry, ammonia here. So I want you to take ammonia, okay, draw the structure for ammonia, describe the bonding interactions between the atoms here, describe the hybridizations of all the atoms involved, okay, and then we'll go ahead and we'll talk about it. Take about 5 minutes, I'm sorry, take about 3 minutes to draw the structure, okay, draw the Lewis dot structure first, okay, and then we'll talk about the angles, then we'll talk about, and then we'll characterize all the bonds. Okay, so let's go ahead and let's do that. Okay, all right. Okay, let's go ahead then, and so this is what we have here. Hopefully you came up with that. Let's see here then how we get that. So the first thing you should do when you draw these structures here, the first thing you should do is draw the Lewis dot structure for the molecule. Okay, so Lewis dot structure for the molecule, then we don't need the three-dimensional structure here. We just need the Lewis dot structure, the two-dimensional structure for the compound here. Okay. All right. So with that said, then you have that's the structure for nitrogen for ammonia. Okay. You don't have to draw all those bubbles. You don't have to draw that, but we have to be able to characterize each one of these here. Okay. So let's first of all talk about the hybridization of nitrogen. Okay. How do we characterize the hybridization of nitrogen? Well, let's count the electron domains first. We have 1, 2, 3, 4. It has 4 electron domains, 3 bonding and 1 non-bonding. But again, that's not going to be relevant for us when we talk about the hybridization here. We have 4 electron domains. Whenever you have 4 electron domains, that will be a tetrahedral configuration. So you have a tetrahedral electron geometry around the nitrogen, which means then that the angles between all the electron domains is going to be about 109.5. So that's your tetrahedron there. Okay, which means then whenever you have a tetrahedral electron geometry, the hybridization here is going to be sp3. So the nitrogen then is sp3 hybridized. So the sp3 hybridization is for the nitrogen. For the hydrogens, remember, hydrogens are not going to be hybridized. So each one of these will have an s orbital, and there'll be a 1s orbital. Okay, so that's our sphere around each one of these here. Okay, each one of these bonds then is going to be a single bond. Okay, it's going to be a single bond, which means then the 2 electrons that are going to be shared here is going to be shared between a sp3 hybrid orbital. Okay, so this is going to be sp3 hybrid orbital here, with an s orbital on this side, which means then this single bond then is going to be a sigma bonding interaction. And some people ask, and they've always asked me in the past, does that mean then that all single bonds will always have a sigma bonding interaction? And the answer there is yes. Okay, so whenever you have a single bond, then it will be a sigma bonding interaction. Okay, so that will be sigma bonding, and this will be sigma bonding as well. Okay, so we have 3 single bonds. Okay, 3 single bonds, all sigma bonding interaction with the overlap between an sp3 hybrid orbital from nitrogen with a 1s orbital from nitrogen. That's how this bond forms. Okay, the electrons are going to move between a sp hybrid orbital and a 1s orbital from hydrogen, which means then the last sp hybrid orbital will be filled with these electrons with this lone pair here. And there it is. That's what you need to be able to do. You don't need to draw the little pictures. You don't need to draw the little animations. You just need to be able to remember what the hybridizations are and think about how the overlap occurs. Okay? All right. Let's try one more here. Let's try one more, and I'll post this for you as well. Okay, let's try one more, and then we'll finish up with this one. Okay. Okay. All right. So let's try this particular molecule here, sulfur dioxide. So take about a couple minutes to draw the Lewis dot structure for this. Okay. I've given you the answer on the bottom. Let's see if you can come up with how you get that. Okay. So let's go ahead and draw the structure for sulfur dioxide. Okay. All right, let's go ahead and let's take a look at the structure for sulfur dioxide here. Okay, so the Lewis dot structure for sulfur dioxide, let's go ahead and draw that out. Okay. It will be, and we did this already, it's going to be a double bond between sulfur and oxygen. Okay, double bond between sulfur and oxygen, the lone pair here. Okay, make sure you're able to do the formal charge calculation to see that this is the best structure for sulfur dioxide, giving us a 0 formal charge on each one of these oxygens. Remember, double bonded oxygen will always be a 0 formal charge, and the sulfur here then will also have a 0 formal charge, which means then Each of these oxygens will have a 2 lone pairs. Okay. All right. All right, so with that said, then let's describe the hybridization around each one of these atoms here. Okay, so we have then for the sulfur, the center atom here, we have 3 electron domains, 2 double bonds, okay, so 2 bonded domains, 1 non-bonding domain, which means then this will be a trigonal planar geometry with 120 degrees between each electron domains. The electron geometry for sulfur is going to be trigonal planar, which means then that this is going to be sp2 hybridized. So the sulfur then is sp2 hybridized, and I hope you see then that each oxygen is also going to be sp2 hybridized as well. So every atom in this particular molecule here will be sp2 hybridized. Okay. All right, so that's what we have there. So with sp2 hybridized, then hybridization, then we're going to have 3 sp2 hybrid orbitals for each one of these atoms. Okay, let's take a look at the center atom here. Okay. And take a look at what we have. Okay. With that said, then I'm sorry, let's go ahead and do the oxygen first. Okay, so the oxygen then, hopefully you see then with the bonding here, it's going to be the overlap between one of the sp hybrid orbitals. Okay, so you have an sp2 hybrid orbital, sp2 hybrid orbital here. That overlap then, which means then that one of the bonds here, it's going to be a linear overlap. That's going to be a sigma bonding interaction, which means then the other bond of the double bond then is going to be an overlap between the remaining electron in the p orbital. So therefore, that's going to be a pi bonding interaction. So you have then 1 sigma, 1 pi bonding interaction, and that's going to be the true for this one as well. Okay, so with a double bond then, people have asked in the past when they've done this enough, does that mean then that all double bonds then will have 1 sigma bonding interaction, 1 pi bonding interaction? The answer then is yes. Okay, and I'll recap this for you towards the end here as well. Okay, after we hope probably at this point then tomorrow, we'll talk about that interaction there and how the bonding type, single, double, or triple, also will correspond to the bonding interactions. Okay. All right, so we have then 1 pi bonding interaction, 1 sigma bonding interaction, which means then the lone pair here will sit in the remaining sp2 hybrid orbital, and these 2 electrons, these 2 electron pairs, these 2 lone pairs will also be sitting in an sp2 hybrid orbital. Okay, and that's how you would you could characterize then the the bonding interactions for sulfur dioxide. Okay, all right. What I would like you to do then is I would like you on your paper to finish out with the krypton difluoride, carbon dioxide, and iodine pentachloride. Tomorrow, what I'm going to do then is I'm going to go over a couple of those with you. Okay, but on your paper for today, at the end of the period, I want you to submit it. I want you to characterize and I want you to draw out the structures for the remaining 3. And when you draw out the structures, folks, this is what I would like you to do. This is the structure that you have to draw. You don't have to draw out all the bubbles or anything. You just have to be able to draw out the Lewis dot structure, characterize the bonds, identify the hybridization of each one of the atoms, okay, and that's it. Okay. So please make sure you do the remaining 3. Okay, do the remaining 3 for number 6 here. Okay, so again, do it for KrF2, krypton difluoride, carbon dioxide, iodine pentachloride, and then I'll pick up with those 3 tomorrow. Okay. All right, folks. Very good. I'm sorry. This afternoon, I have a meeting that I have to go to for AP, and so unfortunately, I won't be able to take any of your questions today after school as well. And I apologize for yesterday not being able to meet with you after school. And so what we'll do is tomorrow, I'll meet with you. If you have any questions about the hybridizations here and the bonding interactions, please come with your questions. Let's make sure you get the homework done for tonight, and then bring your questions for tomorrow. Okay. All right, folks, very good. I will see you. Hopefully, we'll continue with this discussion tomorrow, and hopefully I'll see a few of you tomorrow after school. Okay, have a good day, folks.